Good. Okay. Welcome to the 2008 Rankin series of lectures. It's a great pleasure to have John Baez here from the University of California at Riverside to deliver these lectures. I'll just say a few words of introduction to the lecture series and to John. I'm not going to take up too much of your time because I know we're all passionate to hear John speak. Let me just say, first of all, that I'm grateful to the Board of Trustees of the Glasgow Mathematical Journal Trust for giving its support to this series of lectures. The series was introduced 2 years ago. First speaker was also from California. Yes, Percy Diaconis. His name just escaped me for a moment then. Percy Diaconis, also from California, so I knew John would remember who it is. So I don't know, this is setting a precedent that we'll have many more speakers from California, but it's certainly home to a lot of fabulous mathematics. And we're very pleased to have another Californian back here. The Glasgow Mathematical Trust supports activities that are a little bit wider than just the narrow confines of the business research interests of the University of Glasgow, and positively encourage us to look for mathematical activities that we can undertake which reach out to the wider community in Scotland, and that's very much in the spirit of Scottish education and the history of Scottish education. So that's part of the point here, that John's been invited to speak to us and is expecting to have an audience from a broad range of people with different interests and abilities in mathematics and different kinds of enthusiasms. John is a research mathematician, of course, in his own right, with some 80 publications in learned journals, author of 3 learned books about mathematics and its connections with physics. But for some of us, for me in particular, he's perhaps best known for his enthusiasm and ability to communicate his mathematical knowledge in lively, energetic ways. And for those people like me who enjoy surfing the web to find out nuggets of mathematical information, John's website is one I've come across very frequently, full of bristling with many different ideas about modern mathematics, interconnections with physics. So it's a particular pleasure to have John here in Glasgow this week to deliver the Rankin lectures today, Wednesday, and on Friday. And John's chosen to speak about his favourite numbers, starting with the smallest of the 3 today, the number 5. John.
Thanks. So I'm very honored to be asked to give these lectures, and I hear there's an overflow audience. That's even more exciting. I just want to warn the overflow audience that we actually have a little monitor listening in on you, so if you start snoring, I'm going to go over into that other room and wake you up. So don't think that I can't see you just because I'm not in the same room. So when I was asked to give these lectures, I thought, lectures about mathematics, what should I talk about? And I thought for a while, and then I came up with an idea. I could talk about numbers. And it may seem sort of like an obvious thought to those of you who aren't mathematicians, that maybe a mathematician might talk about numbers, but actually mathematicians think about a lot of things other than numbers. We think about pretty much any sort of structure that we can write down rules to describe, and in fact we get so sick of people making fun of how we're interested in numbers that we like to tell each other, mathematics is not just about numbers. We like to say that over and over again, but mathematics is also about numbers as well as other things. And so I thought it would be sort of fun to actually admit it and to talk about some numbers and to talk about some very specific numbers. I'm going to talk about the numbers 5, 8, and 24. So today I'll talk about the number 5. And part of the point there is that it's a very interesting thing that different numbers have different personalities. In other words, it's as if each number has its own kind of force field radiating out from it that influences the things that it affects, and they interact with each other and do combine in strange ways. And some numbers are more interesting than others. Some numbers do really wonderful, amazing things, and others, they just don't seem to do anything very exciting. Maybe we just haven't found out what's so great about those numbers. But the particular ones I'm talking about are ones that I've thought about a lot because they have a lot of interesting things going on with them. So 5, if I tried to explain its personality in words that have to do with people's personalities, I'd have to say it's difficult, it's sort of awkward, sort of spiky and angular. It just doesn't like to fit in with a crowd. It's sort of rebellious in some way. It's not really the best way to describe the personality of a number, is to use the kind of words you'd use for a person. But that's how I try to say it. And so let me try to explain why that works that way. So the simplest way to see it, I guess, is just to think about what are called regular polygons. So those are polygons with all the sides having the same length and all the angles being the same. So like a 4-sided one's a square. And you can have them with any number of sides that you like, but 5, you'd have to say, is the first rebellious one that refuses to tile the plane. So what do I mean by that? Well, if you take equilateral triangles, you can cover the plane with equilateral triangles. And the reason why is because if you look at the angle of an equilateral triangle, it's 60 degrees, so 6 of them can go around and add up to 360 degrees, and they fit in nicely together there. And so you can just keep laying them out like that in this pattern. And this is a type of pattern you've probably seen somewhere or other. People like to use these patterns for tiles and things like that. Okay, so that's 3. For 4, then you have squares. Squares are even more conformist. I mean, everyone has seen more squares than they want probably by now. People love squares for some reason. And so the angle of a square at the corner of a square here is 1/4 of 360 degrees, namely 90 degrees. So you can fit 4 of them in, and it works out fine. If you go up to 6, well, 6 is also fine because a hexagon, a regular hexagon, the angles are 120 degrees, so 3 of them fit around a corner, and that works out fine. Now, you could go up to 7, but because 3 just barely fit, because hexagons just barely fit, when you get up to heptagons, 7-sided shapes, the angle's too much. So those are too fat, so they don't cover the plane. They don't tile the plane. There's just not enough room, but that's sort of obvious, so we'll excuse them. So 5 is the one that I skipped over, and for 5, the problem is that they're sort of too big and too small. So the angle here is too big for 4 of them to go around a corner, but it's too small for 3 of them to fit around. There's this little gap here. So that's what's the problem with 5 in this case. And so, in fact, you can show that there's no way to make a pattern of tiles that repeats itself in 2 different directions. That's what I mean by periodic tiling, that has 5-fold symmetry. In other words, that if you stand at various different points, you can see in 5 different directions it looks just the same. So 5 is very different than 3, 4, or 6, where you can get that kind of periodic symmetrical tiling. But recently, you can see how old I am. Recently, meaning in 1972, I think of it as recent, Roger Penrose invented non-periodic tilings that have perfect 5-fold symmetry. So if you look right in the middle of this picture, in all 5 directions going out from it here, you have the exact same view. So this is made up out of 2 different kinds of shapes, 2 different kinds of rhombuses, rhombi. But it's not periodic. This pattern never repeats. It can't repeat because it's a theorem that you can't have a periodic pattern with 5-fold symmetry. So he sort of broke the rules and said, well, let's look at a non-periodic pattern, and found that. But in fact, there's also other things you can do. You can take the same kind of tiles. These are the same kind of 2 tiles, And you can just start putting them together sort of any way you want, and this you can get all sorts of sort of random patterns that have approximate five-fold symmetry, meaning that if you look in certain directions, you'll see, well, like here, you see that like in some directions you have things going this way, this way, this way, this way. I can say a little bit more about what I mean by approximate five-fold symmetry, but this pattern has some kind of fiveness to it, but it never repeats. So that's something you can do. Turns out that people weren't really the first people to discover this. Nature was the first one to discover this. So it turns out that just like in the plane you can't have five-fold periodic symmetry, also in 3 dimensions you can't have crystals that repeat in 3 different directions that have five-fold symmetry. But in the 1980s, after Penrose invented mathematically the possibility of these non-periodic patterns, physicists and chemists discovered certain things that are now called quasicrystals that have approximate five-fold symmetry. So there's sort of building blocks, little bits of molecules that you could fit together, that just fit together on their own, to form patterns that don't quite repeat but have five-fold symmetry. What this thing is here is it's called a diffraction pattern formed by shining electrons at the crystal and seeing how they bounce off, or they may go through it and get pushed a little bit in one direction or another. And so most of them go straight through it, and that's this big bright dot here, but some of them get pushed off in different directions. And if you look around this big dot, you'll see 10 little dots coming around it, or also these ones here. There'll be 10 of them. So there's 10 is 2 times 5, so there's some five-fold symmetry to this diffraction pattern, and that's saying that there's sort of 5 different directions that this quasicrystal thinks of as equally good, but it never quite repeats itself perfectly, the crystal. This isn't a picture of the crystal, notice. This is the picture of the electrons that have bounced off the crystal. So it turns out that nature beat Penrose to the punch, but in fact, actually, it turned out in 2007, people noticed that there had been Islamic tile designs in various mosques and things that have five-fold symmetry, using ideas very much like Penrose's, but came much earlier than him. So in fact, someone is able to write and publish a paper about this, which seems a little odd in 2007 to write a paper saying, there's this church, it's been standing here for 400 years, and I finally looked at it and saw that it had these nice patterns on it. So this is the actual photograph, and this is sort of a mathematical simplification of it. So they sort of remove some of the decoration, so you can see more clearly that, like right in here, for example, this shape here has 10 different directions that are all the same. And you notice that this, well, I'll have to convince you that this doesn't perfectly repeat itself. Maybe it looks like this thing is perfectly repeating itself here, but then if you look up further, you see, no, it's not quite repeating itself up there. So it can't possibly repeat itself perfectly periodically, but it does a very beautiful pattern anyway. Here's another one in Iran. So again, this is just standing out there in the open for everybody to see, but people hadn't quite necessarily noticed that it has a lot of five-fold symmetry to it. So those quasi-crystal patterns are actually very interesting these days, and they have a lot to do with fiveness. There's another thing you can do, which is to say, well, okay, this stupid thing, it doesn't quite tile the plane, but I can take advantage of that. I can fold up this pattern here and get a three-dimensional shape. So you take advantage of these cracks here to fold the thing up into the third dimension, and you get a shape called a dodecahedron. So I happen to have one, just by chance. And so this is a 12-sided shape here, because it has a side on top and then 5 around it, and then a side on the bottom, exactly opposite, and 5 around it, so for a total of 12. So dodeca means 12. So that's 12 faces, but each one of them is a pentagon, And if you count more things, you can see that it has 20 corners and it has 30 edges. And it's called a platonic solid or a regular solid because every face looks exactly the same. Also, every face looks exactly the same after you turn it. That's because it's a regular polygon. But also, every corner looks exactly the same. Every corner keeps looking the same as you turn it. And also, every edge looks the same. So that's what a regular polygon or platonic solid is. And it's one that has a lot of five-fold symmetry. In other words, I can take it and I can hold it some way, and then I can turn it 1/5 of a turn, and it should come back to looking just the same if you didn't count all these different colors on the sides. And so after 5 turns, it's back to where it was. That's an interesting shape. It can't happen in a crystal because crystals can't have five-fold symmetry. So it's an interesting question. Can you find this kind of shape in nature? And the answer is yes. For example, you can find it in certain viruses. So there's a virus called the virus that has, well, on the outside it looks just like this blob here, but if you look on the inside, it has a dodecahedron made of RNA, made of the genetic material that a virus is. A virus is just a little gizmo with a protein coat and RNA or DNA on the inside, and what it does is it latches onto a cell of an animal or a plant. It burrows into the cell, and it sort of hijacks the machinery of that cell to reproduce its DNA or RNA. So it's sort of like the minimal possible self-reproducing biological entity. It doesn't really do anything except reproduce itself. It doesn't have any metabolism. It just has to use something else to help it out in the reproduction process. And this is very small. This is 10 nanometers long. That's 10 billionths of a meter. This line here, this is a blown up view of the thing. That's 5 nanometers long. So that's a dodecahedron in nature. It's not the smallest dodecahedron in nature. There's actually a molecule called dodecahedron. I don't know if that's actually found in nature, I should admit. It's been synthesized by certain chemists who like to do this kind of thing just for fun, you know. What do you do on a rainy day? Well, let's try to make some new chemical. So it has, if you look at it, it has 20 carbon atoms, which are these, shown as these sort of big bluish things, and then it has 20 hydrogen atoms as well. So all the carbon atoms there form the corners of a dodecahedron, and also all the hydrogen atoms form the corners of a larger dodecahedron. It's interesting to look at the journal where they describe how they made this stuff. It actually reminds me of what I was doing today. I didn't take this thing on the plane when I came over here. I had to assemble it today. I had to stick in all these pieces together. But these guys were a lot better than me because they were able to coax these molecules by some sequence of reactions to sort of build themselves up into forming a dodecahedron, which is just shows you how good chemists are these days to dream up reactions that will build pretty much anything that's possible. If you want something in nature, that's, I think, the most common thing that's like a dodecahedron is soot or carbon dust in outer space. So it turns out that it naturally forms this pattern here, sometimes called a buckyball, after Buckminster Fuller. So Buckminster Fuller was an engineer who designed the geodesic dome, and if you took, well, this is also the pattern of a soccer ball. If you notice, it has some pentagons, which would be black in a soccer ball, football, and it has some hexagons, which would be white. But way to think of it is it's what you get by taking a dodecahedron and chopping off certain corners of it to make this more fancy pattern. And chemists at some point did a whole lot of work to synthesize this molecule, but then later on they discovered that if you just have a candle and you stick a spoon over it and some black soot forms on it, a lot of that stuff is made of this. So it turned out they didn't need to do so much work to make it. And in fact, they found that if you look around certain stars near the end of their life, they shoot out huge amounts of carbon. And now we can just, using spectroscopy, see that a lot of that carbon is in the form of this stuff. So there are these dodecahedron, or buckyballs, floating around out in outer space just naturally. What about humans and dodecahedra? Well, of course, the earliest human-made dodecahedron is Scottish, as you would expect. So here it is, right here. So these are some carved stone balls which have been found in various parts of Scotland and northern England that date back to around 2000 BC. And they come in all sorts of patterns, not just these types of patterns, but a lot of interesting geometrical patterns. No one has any clue, as far as I know, what they were used for. But these 5 here are modeled after what we call the Platonic solids, although Plato came a lot after this, so it really shouldn't be called that, I guess. But this is basically a dodecahedron with these pentagons. This is basically an icosahedron. It's called with 20 triangles. They're sort of rounded out and bumpy in these models. This is called an octahedron. It has 8 triangles. This is modeled after a tetrahedron. It has 4 triangles. This one's pretty wiggly here. And that's basically a cube. So sometime somebody should figure out why they were doing this. Maybe just for fun, I guess, but no one knows. So those were discovered fairly recently. If you'd asked people maybe 30 or 40 years ago who invented the dodecahedron, they would have said it was the ancient Greeks, because Plato wrote about it, wrote about that shape. And some people have theories that they were inspired to invent the shape of the dodecahedron by looking at crystals of fool's gold, or iron pyrite, which look like a dodecahedron. You'll notice those look like pentagons, and it looks like 3 around each corner. But the interesting thing is that fool's gold, true to its name, is really just fooling you into thinking that it's a regular dodecahedron, because no crystal can really be shaped like a regular dodecahedron. Fool's gold is actually a cubic-shaped crystal. The molecules form this cubical pattern, and you can approximate a dodecahedron out of little cubes, as shown here. But it's not really right. If you look at these pentagons and you stare at them carefully, you see that they're not really a regular pentagon. But so it's possible that the Greeks, because they liked everything to be mathematically beautiful and perfect, they looked at those iron pyrite crystals and imagined or came up with the idea of a perfect regular dodecahedron. That's a theory that some people have. No one's really sure about that, actually. The Greeks had colonies in Sicily, and there's a lot of iron pyrite there, and there are also a lot of Pythagoreans there. Pythagoras is a semi-legendary mathematician. It's believed that pretty much everyone believes he really existed and lived in around 500 BC, but people know very little about what he actually did. There are huge amounts of myths and stories about what he did, but if you try to track down those stories and find out if they're really true, they all sort of dissolve in your hand. A lot of those stories you find were like stories that people made up several hundred years after he died. But it's known that there was a kind of cult, a vegetarian radical cult of mathematicians called Pythagoreans, who actually gained quite a bit of political power in Sicily before they were all booted out, and a bunch of them may have been killed, in fact. And they had strange ideas. They thought that everything in nature was fundamentally mathematical, and there are stories that they were very interested in the dodecahedron, and that they had some kind of religious or some kind of ritual where they would take the initiate, the budding Pythagorean, the young Pythagorean, and describe to them mathematically what a dodecahedron was like, not actually show them a dodecahedron, and then force them to imagine in their mind what a dodecahedron was like, to test their powers of visualization. And then when they finally succeeded or whatever, then they would actually show them a dodecahedron. And then it would blow their minds. And then they would join the cult. So as you can see, I'm sort of trying to round you up here to join the cult. The Pythagoreans were also fascinated by the five-pointed star, also called a pentagram, which the later Christians thought was a demonic symbol. But the Pythagoreans seem to attribute magical properties to it. This is actually a picture made by some much later Pythagoreans of a pentagram. And the pentagram is a really interesting illustration of some of the sneaky properties of the number 5. So you may have looked at a pentagram a lot of times, but may never have really looked at it carefully. So here I have a regular pentagon, and then I just draw all these lines going between all the corners to get a five-pointed star. But if you look carefully, you see there are lots of triangles in there. And in fact, there are 20 triangles that all have the same proportions, all the same shape. Namely, there are 5 that look just like this red one and different rotated versions of that. There are 5 that look like this blue one pointing this way, but there are also 5 that look like the blue one that you can't see that would be pointing the other way. So that's a total of 10 blue ones. And then there are 5 of these green ones. And they all have the same shape. And that's an interesting shape, actually. It's an interesting triangle. There's something special about that shape of triangle because of the following thing. So here what I've done is I've taken one of those triangles, this big triangle here, and I've chopped it into 2 smaller triangles, a green one and a blue one. And you'll see that this green one is the same shape as the whole big triangle. I could prove that geometrically, but I don't feel like doing that. That's a fun little exercise to prove that this little triangle has the exact same proportions as this big one. But if you believe that, then you can see some interesting things. So let's make up some names for how long these different edges are. So let's call this edge here length 1. And let's call this longer edge here phi, which is a funny name for a number. It's also called the golden ratio, which we'll see why it's so great in a minute. So that length there is the same as this length here, because they're both just the longer edge of one of these kind of triangles that I'm outlining here. So that's phi, but that's also phi. So this whole long edge that I'm outlining now, that has length 1 plus phi. But that has the same length as the one on the outside here. So this is 1 plus phi. All these triangles are isosceles triangles, right? So the length of this is the same as the length of this. So if you stare at that, you can see something interesting. The shape of this little triangle is the same as the shape of this big triangle. They're different sizes, but same shape. So that means the ratio phi divided by 1, which I've written over here, has got to be the same as the ratio 1 plus phi divided by phi, because they're in proportion to each other. So phi is to 1 as phi plus 1 is to phi. So that's the magical property of this number phi. And if you want, you can take this equation and multiply both sides by phi. So over here on the left you get phi squared, and on the right, I just did this to get rid of this denominator here, you get phi plus 1. So the equation that the golden ratio satisfies is that phi squared is phi plus 1. So it's a number that's positive, and if you square it, it's the same as adding 1 to it. That's what it is. If you know how to solve a quadratic equation, you can solve this quadratic equation and figure out what it is. And it turns out to be 1 plus the square root of 5 over 2. So the 5-ness of the pentagon actually sneaks into the 5 here in the golden ratio. And you could think a lot more about why that really works that way, but it certainly does. And you can plug it into your calculator and you can figure out what it is. And it's 1.6180339 ... And then if you don't believe me when I say that phi squared equals phi plus 1, you can take that number and you can square it, and your calculator, which never lies, will tell you it's 2.6180339. So it's really true that it satisfies that equation. But it's a marvelous number. It shows up in lots of different ways, and it has lots of nice properties. For example, I can take this equation here, and I can divide both sides of this equation by phi. So if I divide phi squared by phi, I'm left with phi. If I divide phi by phi, I get 1. If I divide 1 by phi, I get 1 over phi. So phi is 1 plus 1 over phi. Or in other words, if I just fiddle with this equation a little bit more, 1 over phi is the same thing as phi minus 1. So the other nice thing about this number phi is if I take its reciprocal, 1 over it, I just get 0.618, 0339. So it keeps sort of showing up when you keep fiddling around with it in different ways. That same decimal expansion shows up. Now, there are lots of interesting things about it, and probably the most interesting thing to me has to do with this idea of continued fractions. So the Greeks liked to study fractions in a certain way called continued fractions, and here's how it goes. So I'll just take some number, some fraction, I made up some crazy one, 74 over 32, and then here's what we'll do with it. We'll divide 74 by 32, and we'll get 2 plus some leftover stuff that's smaller than 1. So we get 2 plus something, and that something just happens to be 10 over 32. And then what we'll do is we'll take this leftover part, this remainder part, that's less than 1, so we'll write it as 1 over something that's bigger than 1. So 32 over 10 is bigger than 1. And then we do the same thing. In other words, this number is bigger than 1, 32 over 10. So now we write it as a whole number plus some leftover stuff. So 32 over 10, you can see, is 3 plus 2 over 10. So then what do? We just keep doing the same thing. 2 over 10 is the same thing as 1 over 10 over 2. And now we take this number 10 over 2 and we write it as a whole number plus some leftover stuff. But in this case, it stops. 10 over 2 is a whole number. It's 5. So we quit there. And so that's called the continued fraction expansion of this fraction, and it quits at this particular point. So if you take any ratio of whole numbers, you can play this trick to it, and you get this way of writing it called its continued fraction. And it stops at some point. Euclid, there's something called Euclid's algorithm that you may have heard of if you've taken fancy math classes, and it's based on this idea that it stops at a certain point. But if you take the number phi, it never stops. Because, as I said, phi is 1 plus 1 over phi. That's one of those equations I wrote down. So if you're some poor schlep who's trying to work out the continued fraction of phi, you'll say, okay, phi is 1 plus 1 over some extra stuff. Then I have to do the same continued fraction trick to that phi. Well, what is that? Well, phi is 1 plus 1 over phi. And then I have to do the same thing there. So I get 1 plus 1 over 1 plus 1 plus 1 over phi, and it goes on forever. So it never stops. And if you have already convinced yourself that when you have a fraction, a ratio of two whole numbers, that this process must stop, then with this number here, where it never stops, it can't be a ratio of two whole numbers. So it has to be what's called an irrational number. There's a story that when the Pythagoreans when there was some Pythagorean who first proved that some number was irrational, and they say that he first proved that the square root of 2 is irrational. The story goes that some other Pythagoreans took him out on a boat and drowned him because they liked rational numbers so much. They just didn't want to hear about this. It was like an unsuccessful cover-up of the existence of irrational numbers. And the way that the story is usually told, it was the square root of 2 is like the first one that they found that was irrational. But it's possible, since the guy drowned, who knows what he really discovered. It's possible that it would be phi that he discovered was the first irrational number, because it's so easy to show that it's irrational if you know about continued fractions, which the Greeks did. And in fact, the Greeks really liked proofs using geometry. They didn't really write down fractions the way we did. But in fact, you can even just look at a pentagram and stare at it. And if you stare at it hard enough, in the right way, you can see from it that the continued fraction expansion for phi never ends. And so something that some people wonder is whether just that would be enough to let them see that phi was irrational. So how do you actually, well, I don't know if the Pythagoreans knew this. I'm just sort of making this up. Okay. If I was a typical historian of mathematics, I would just claim it was true. Mathematics is one of the hardest subjects to do the history of, because if you see something is true, it's just hard to believe that someone else couldn't see it too. And so the historians of mathematics say, well, like, of course they must have realized this. And so they just make stuff up, in other words. But since I'm not a historian of mathematics, I guess I'm not allowed to do that. But I'll still make up this thing here. My friend James Dolan drew this picture. So what is this thing? Well, it's just a big black pentagram, but I'm not trying to initiate you in some satanic cult. I'm trying to show you something here. Namely, if you take some of the corners of this big black pentagram and start connecting them up with lines, you get these lines, and those lines form other pentagrams. So I just got this blue one here by connecting up the corners of the black one. But then I can do other stuff. Let's see, what's the next good thing to do? Well, for example, I can take these two corners of this blue one. I can draw a straight line through it, which is this green line, and I can extend that all the way out to here, and all the way out to here, and so on. And then I can start connecting up those things with lines, and so I get all this stuff. So if someone hands you a picture of a pentagram and all you have is a straight edge, you can just start drawing more straight lines, connecting dots that you already see, and you can form this whole big picture. And you'll notice that it's full of pentagrams of all different sizes. In particular, for example, you can see this blue one, and then there's a smaller green one, and then there's a smaller blue one, and then there's a smaller green one, and then there's a smaller blue one, and then there's a smaller green one, and they shrink away forever like that. And the interesting thing is that the ratio of the sizes of, say, like this green one here to this bigger blue one, the ratio of the sizes of two of those is the golden ratio. It's phi. And the interesting thing is that you can see that the main equation holds for phi in the following nice way. So take this length here and convince yourself that this length is the same as this length. That's the next smaller pentagram there. This length plus this length, which is the next smaller one. They alternate blue and green. So why is this big line as long as this line plus this line? See, that fact is the same as the fact that 1 plus phi is phi squared. Each time these lines are getting bigger by the same factor. But it's not just that each one is getting bigger by the same factor. It's that each, as you go along, the small one plus the next bigger one is equal to the length of the next biggest one. Well, it's actually really easy to see why that's true, because here's why. So if we take this long one here, we can chop it right here. And then this long part of it is just as long as this one here. And then the rest, this part here, is just as, if you just draw a parallelogram, if you just go up here, you see it's just as long as this one. So if you stare at it for a while, you can see it's just obvious that all these pentagrams are, as you climb up to the tips and get smaller, they're all getting smaller and smaller by a constant ratio, but that ratio has the property that 1 plus phi is phi squared, because I'm saying that 1 plus phi is phi squared. And in fact, the fact that this thing never stops, the fact that it keeps on going on and on and on forever, you can see, if you scratch your head a bit longer, that that's the same fact as the fact that the continued fraction expansion of phi never ends. So that if you were a smart Pythagorean, you could just stare at this thing for a few weeks or months or years, and you'd conclude that the golden ratio, so-called golden ratio, had to be an irrational number. And what do you get for it? They throw you off a boat and drown you. So that's what we get. So in fact, it's not just true of the golden ratio that the continued fraction expansion never ends. For any irrational number, it never ends. And for any irrational square root, it repeats in a very nice way. It gets stuck in a loop. It starts repeating. So for the square root of 2, that turns out to equal 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2. Square root of 3 is 1 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 2. So this one goes, after a little while, it starts going 1, 2, 1, 2. So they all these irrational square roots, they have sort of cute continued fraction expansions. But what's special about the golden ratio is that it's the simplest one of the lot. The golden ratio is the very simplest one. It just has all ones. So you wouldn't have necessarily expected that the very simplest one of all these guys would be the square root of 5 plus 1 over 2. But that's true, and that's what's sort of special about the number 5, really. That's what the 5-ness of the pentagon is making, and the pentagram is making the golden ratio be the very simplest of all the continued fraction expansions. And there's a certain way in which it's the most irrational number, meaning that it's very hard to approximate the golden ratio very well by nice, simple, rational numbers. Let me show you why that's true. So the way you get a really good approximation of a number by a fraction, by a rational number, is to take its continued fraction expansion and then just quit at some point and then figure out what fraction you've got. And this way of getting a good approximation, it works really well when you quit right after you hit a really big number. So it's easiest to explain by an example. So this is the continued fraction expansion for the number pi. So you know pi is like 3.14159, blah, blah, blah. But you can also write it out as a continued fraction expansion. You can work it out, and it's 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over 292 plus 1 over something and something. And this one doesn't satisfy any pattern. No one knows what the pattern is. It's just some crazy bunch of numbers. But 292 is, of course, nice and big, so it might be fun to stop then. In other words, say, OK, I quit. I'm just going to stop there. And I won't get exactly pi if I stop there, but I'll get some number that's hopefully pretty close to pi. So let's do that. Well, actually, you could quit way before then. You could say, I'm going to quit as soon as I get to 7. 7's pretty big, so I'll just stop there. So I'll say pi is about 3 plus 1 over 7. Well, that gives you an approximation to pi that people talk about a whole lot. At least they used to before calculators were invented or something. So 22 over 7 is a sort of famous, pretty decent approximation to pi. It's 3.1428, which isn't too bad. It's got 2 decimals right. But if you wanted to do a lot better, you could say, I'll work a bit harder. I'll go down to this 292 here, and I'll quit then. So I'll take this big thing here, and I'll work out what it is. You just grind away. You work it out. It's 355 over 113, which is sort of cute, right? Because it's like 113,355. That's just a coincidence. It doesn't mean anything. But anyway, what the heck? You know, take advantage of it. So. But the neat thing is that that's an incredibly good approximation to pi. It's 3.1415929, blah, blah, blah. And pi is 3.1415926, blah, blah, blah. So it gets the first 6 decimals right. And interestingly, it was discovered in 480 AD by a Chinese mathematician, Zhu Shangqi. So clearly some people had lots of time on their hands back then. Now, if you take the golden ratio and you try to do the same kind of thing, you're never going to hit a big number in the continued fraction expansion. It's just all ones. So it works very slowly and pathetically. So the first approximation gives you 2 over 1, which is 2. The next one gives you work it out, you get 3 over 2. then 5 over 3, 8 over 5. So these numbers here, they're wiggling up and down. 2 is big, 1.5 is small, this is big, that's small. They're wiggling up and down, getting closer and closer to the golden ratio, which is 1.6180339, blah, blah, blah. But they're going very slowly, and to actually get 6 decimal places right, you'd have to go a lot further out than you do for pi. You'd have to go to 1597 over 987. So that's what I mean by saying that the golden ratio is the most irrational number. You can actually be more precise than I want to be right now and say and prove that the golden ratio is sort of the hardest number to find good approximations of by fractions. These fractions are actually famous. If you've ever studied some numbers called the Fibonacci numbers, that's what's showing up here. But that's a whole other story, and I don't think I want to talk about Fibonacci and his rabbits and all that stuff. Instead, what I want to say is what's so great about the fact that the golden ratio is the most irrational number. The point is that nature likes rational numbers. For example, if you have a nice chord like an octave, it's because 2 people are singing or 2 piano strings are vibrating at 2 different frequencies. One is wiggling just twice as fast as the other. So an octave just means one thing is wiggling twice as fast as the other. Or a fifth, which is another really nice sounding chord. Da 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 da. You just go up 5. I probably went up 6 because I can't count. But if you go up 5 up the scale, turns out that the high pitched one is just 1.5 times. It's wiggling 1.5 times as fast as the slower one, 3 halves. So those are nice rational numbers, and and they sound nice because actually it's interesting to think about why they sound nice. They sound nice because of stuff about the physics in your ear. If you hear one of those sounds, it wiggles the little hairs inside the cochlea of your ear, but that tell you what pitch you're hearing. But because of this effect called resonance, it also wiggles the hairs that want to wiggle at some other speed that's related to the speed that you're hearing by some rational number. So if you hear a sound, your ear also sort of hears as if it was hearing an octave higher or a fifth higher. And so that's why when you play both of those sounds, your ear is particularly happy. It sort of goes, oh, yeah, it's working. And it's just a purely physics mechanism, which you can see more easily by taking a piano, holding down the pedal, and like plucking or pounding one of the notes, and then like cover up all the strings except for the note that's 1 octave higher, and you'll hear that that one has got wiggling too. So in other words, when you wiggle something, it makes anything near it that can wiggle at the same speed want to wiggle too. But also things that wiggle twice as fast, and also things that wiggle like 1.5 times as fast, or 4/3 as fast. Any nice fraction will do, because basically one vibration will sort of get the other vibration going in sync with it, and if they match every 3rd time or every 2nd time, that's good enough. And this happens all over the place. So this is a picture of a little portion of the rings of Saturn. It's a real close-up of the rings of Saturn. And people have been studying the rings of Saturn and noticing, so what is the rings of Saturn? It's a bunch of dust and rocks going around in circles around Saturn, ice, but it likes to go in certain places much more than others. So here it's bright because there's lots of stuff there, but right here it's dark because there's not much. And the pattern that the rings of Saturn form is incredibly complicated. As you can see, there are lots and lots of these stripes, and it's not coincidence or anything. It's a very complicated mathematical pattern. And the reason is that if you've got a moon going around Saturn, and Saturn actually has a bunch of moons, but if you take one of the moons of Saturn, then any little piece of dust that would be going around some orbit that had a frequency that was some nice rational number times the frequency of your moon, it'll tend to get in resonance, and it will tend to actually get pushed out of its orbit. So this black area, this relatively dark area here, for example, is called the Cassini division. It's a certain thing that the astronomer Cassini, who was one of the first to study the rings of Saturn, saw. He just saw that, hey, look, there's a black circle there. It means that there's not much stuff there. The reason why is because stuff that would be there would be going around just exactly twice as fast as a certain moon of Saturn called Mimas. And all these more complicated patterns are coming from more complicated rational numbers. But the point is, the golden ratio is the furthest away, in some sense, from any rational number. It's the hardest to approximate by rational numbers that are simple. And so the golden ratio is sort of the most stable orbit. Things that are related by the golden ratio to some moon are the most stable, and so you'd find a lot of stuff there. And people have observed that phenomenon in a lot of situations. So it's far away from being in resonance with any rational number, so to speak. So you could say it's because 5 is sort of awkward. It doesn't match up very nicely with any rational number. Here's another example of how the number 5 is sort of awkward. You could say, well, okay, I didn't succeed in tiling the plane with pentagons, but when I tried, at least it folded up to form this nice shape, the dodecahedron. So maybe I can fill up three-dimensional space with these guys. I can take a bunch of these guys and pack three-dimensional space with them. But if you try to do that, that doesn't work either. You get these annoying little cracks here. So like it comes darn close to perfectly fitting, but it doesn't quite work. And so that's another example about how like nothing quite matches when you're dealing with a number 5. But you could say, well, okay, tough. I'll just keep on going ahead. It didn't quite work, but I'll just stick on another layer of these dodecahedra anyway, as if I was still. So I'm putting on a new layer of these guys onto the ones that I already had and matching them up perfectly on these pentagon faces. Of course, now the cracks are getting worse, so you may wonder why I'm doing this. Well, I'm building up the suspense. That's what I'm doing. And so then I stick on another layer. Well, it's getting even more worse. There's getting to be lots of room. And another layer. Well, it's getting even worse. And then I'll put on one more dodecahedron, not a whole nother layer, just one more. So you notice that's just this, well, it's hard to tell, but that's just the same as that with just one more. And now if you count them, obviously there are exactly 120 of them. And then you can say, okay, what's so great about that? Well, here's what's so great about that. So I said that with the dodecahedron, if you tried to tile the plane with pentagons, it didn't work so well, but if you curl it up into the third dimension, then it fits together into this beautiful shape. So now here, similarly, this thing is a mess. It didn't really work. But if you curl it up into the fourth dimension, then you get some great thing. You get what's called the 120 cell. It's a four-dimensional shape that has 120 dodecahedra. And, well, you may not be used to visualizing four-dimensional things, but take my word for it. You can do it. You just need to imagine some direction that's at right angles to every one that I can point at. So it's just sort of like imagine it's over there or something like that. Don't and somewhere where you're not looking too carefully, and so the surface of this 120 cell will be like a sphere, but in the fourth dimension. So there'll be like 4 different directions you can go, and it will be covered with 120 of these guys. Now, how do you visualize it, though? I am trying to fool you into imagining that you could visualize it. Well, it turns out there's another way to try to visualize it. So the surface of it is a kind of sphere, but it's not a two-dimensional sphere. It's not a sphere like the normal. Mathematicians call this thing a two-dimensional sphere. Why is it called a two-dimensional sphere? Because it takes 2 numbers to say where you are on the sphere, like the latitude and longitude. So mathematicians would say a 3-dimensional sphere is the surface of a ball in 4 dimensions. So if I was on a 2-dimensional sphere, like on the Earth, in fact I am on a 2-dimensional sphere, I could walk in any direction, and if I was patient enough, I'd loop around and come all the way back. I won't demonstrate that now, although you may wish I would, but I'm not going to. So similarly, it's possible that the universe is a 3-dimensional sphere. No one knows, in fact, if it's true or not, but it's possible, and there's no evidence to rule it out. What would it mean? It would mean that if you took a spaceship and you just shot off in some direction and went on and on and on and on and on and on, then millions of years later, you'd appear, but coming back from the other direction, coming from there. So like if I shot up there, and you wait, I come back up from here. So that's the idea of a three-dimensional sphere. So we could be in a three-dimensional sphere for all we know, and that's nice because then you can imagine what the surface of this 120 cell would be like. It would be like being in here, being in the surface of this thing, but it would be chopped up into 120 dodecahedra. And that's something I can actually show you a picture of. So it would look like this. So this thing has 120 dodecahedra separated by these pale blue bubble membranes. They look curved, these surfaces, but that's because I've tried to take this three-dimensional sphere and stick it into a three-dimensional normal space, which isn't a sphere, at least on such short distance scales. It's not a sphere. So it's more or less flat in this room or on this picture. If you actually counted all these bubbly things, you'd be upset at me because you would only see that there are 119 of them, not 120 of them. But the reason why is the 120th one is where? Where's the 120th one? It's the outside. Yeah, the rest of it, all this stuff on the outside, is also a dodecahedron. It has 12 of these pentagon faces. So we've chosen to take one of them to be the outside, and then the rest of them to be the inside. This is a nice thing. So people have been wasting their time when they should be at work making pictures of this thing, which I can just freely download because they're all on Wikipedia, and I'm allowed to do it. So this is one that's made in some kind of sort of rubbery model. And this is actually my favorite one here. This is made out of shiny titanium with gold spheres holding it together. So that's another picture. And you'll see that these dodecahedra, they don't look like regular dodecahedra. They look quite warped. Like this side here is a lot bigger than those sides. But that's because we've tried to take this thing that really wants to be evenly spread out around the surface of a three-dimensional sphere and squashed it into this little flat piece of space that we see in this picture. So it's sort of a warped image of the real thing. And that's the best we can do right now. And I want to wind up by telling you another way to get at this shape. So this is supposed to be the part of the talk that doesn't make any sense. There's a tradition in math talks where like you start out saying stuff that makes sense to everyone in the room, and then like halfway through you switch, you get more advanced and you talk so that like only half the people in the room do it. And then you keep doing that until finally even you don't know what you're talking about, but no one else knows, see, so it's okay. So this is going to be like that part. So in other words, you're not supposed to be upset if you don't understand this. You're supposed to think, I went to like a real math talk, just like a real professional math talk. So the dodecahedron has some 60 things. There's 60 ways to take a dodecahedron and turn it so that it comes back to being in more or less the same position, but maybe the faces have gotten mixed up. So for example, I could put my fingers on any face and the opposite face, and I could turn it a fifth of a turn, and it would come back looking more or less the same shape. Let's see if I can actually do that. So like that. Those are called rotational symmetries of the dodecahedron. So I could do that in 5 ways there, but I had a choice of something. I'm getting really confused right now. I see. I guess I already reached the point where even I don't know what I'm doing. There are 12 of something. Yeah, I was thinking about it a slightly different way here. I was thinking that I could take. Yeah, I should read this slide here. So I could, with a rotation, I could carry any one of these faces to any other of the 12, or itself for that matter. But I could do that in 5 different ways, because there'd be 5 ways it could wind up being rotated. So there are 5 times 12 ways to rotate this thing that are the symmetries. And that's 60, which is half of 120, the 120 that shows up in the 120 cell. So you may say, is there some relationship between that 60 rotational symmetries of the dodecahedron and the 120 dodecahedra in the 120 cell? And it turns out that there is a relation. But what's that relation? Well, there's an interesting thing. There's a kind of particle called a spinor. And an electron is an example, and so is a proton. And it's discovered something amazing about them, namely that if you take a spinner, one of these kind of particles, and you turn it around 360 degrees, it doesn't come back to where it was. You might think that if you turn something around 360 degrees, it has to be exactly where it was. That's common sense. But it turns out it's not true. That's called higher education. And so it turns out that if you turn it around twice, it does come back to where it was. That's an amazing fact that was discovered as part of the whole idea of quantum mechanics. And I'm not going to try to explain that, but I could if I wanted to. And so the point is, if I had a dodecahedron that was a spinner, there would be a difference between turning it around 360 degrees and not. So there would be twice as many different symmetries as you might naively and sensibly think. So there'd be 120 symmetries. And it turns out that each of those 120 symmetries of the spinner dodecahedron, let's call it, is the same as one of the dodecahedra in the 120 cell. So that's a very strange combination of ideas. And you can sort of begin to see it's true because of all these symmetries, each one of them has 12 nearest neighbors. So there are tons of ways to rotate this thing, but each way to rotate it has 12 different ways that are really similar, namely, do that rotation, but then just rotate 1 extra fifth of a turn. That's just slightly different. That's the closest thing you can do to not doing anything at all, is rotate this thing 1/5 of a turn. But you could do that 1/5 of a turn around 6 different axes, and you could go either clockwise or counterclockwise. So there are 12 nearest neighbors to each of the rotations of this spinner dodecahedron. But they're also, going back to this picture, there are 12 nearest neighbors for each of the dodecahedra in this horrible thing here. So it turns out, I should have just done that. So it turns out that this 120 cell, among other things, it's also a picture of all the rotational symmetries of the spinner dodecahedron. So each of the dodecahedra in this picture is also a rotational symmetry of this spinner dodecahedron. So that's just an example of how things can get fairly elaborate and interesting when you start messing around with math in general or the number 5 in particular. And Rankin, who I'm lecturing in honor of, he actually spent a lot of time studying papers by this Indian mathematician Ramanujan. And what Ramanujan did is just write down insane formulas and say, I know this is true, and then leave it to other people to figure out why. And this is one of the ones that I really like. This is one of the Ramanujan continued fractions. So this is a weird continued fraction where you have 1s down here, and then e to the negative 2 pi, e to the negative 4 pi, e to the negative 6 pi, and so on. And he wrote this down. That's equal to, obviously, the square root of 5 plus the square root of 5 over 2 minus the golden ratio times e to the 2 pi over 5. So there's something really cool about this because this right-hand side is very 5-y. There's like 5s bristling all over the place with it. This doesn't seem particularly 5-y at all. So it shows, excuse me, that there's some deep and mysterious ways in which the number 5 can show up. And I hope someday I really understand why this formula is true. I have a paper about it that I got off the internet that explains it, but I don't understand it. So in any event, I dedicate this lecture to him, and thanks for listening to me.